All right. Welcome, students. Welcome back to Chemistry for Everyday Life. So this week, we are in a fourth unit. We're going to take a look at electrons and ionic bonding. So last week, we talked about the atoms and the subatomic particles, and we talked a little bit about electrons because it is one of the subatomic particles. So this week, we'll dive a little bit deeper into the electrons because it turns out all of chemistry minus nuclear chemistry, the main actor are the electrons. Right, so as a review, last week we talked about J.J. Thomson's view of the atomic model called the plum pudding. So where he imagines that the atom is basically a mass of positive charge, and on this and in this ball there are sprinkled out throughout, evenly distributed throughout, are negative charges. Okay, and then this idea was further refined with this gold foil experiment by Ernest Rutherford, where no, he said that that mass is actually very small and it's right in the center of the atom, and he defines it as the nucleus. And so the nucleus is the massive part where it has positive protons and also neutral neutrons. Now, outside of that nucleus lives the electrons, and the electrons are very small in mass, but they take most of the space of the atom. Okay, so they live outside in this thing called the electron cloud, and then it turns out it's mostly empty space that is part of this atom. Okay, and from there, the model is built on further by Niels Bohr, where he says that these electrons not only live outside, but they live in different levels. And at this time, the idea of the solar system was just being discovered, and so it's very similar to the solar system, where you have the sun in the middle with planets orbiting the sun. Just like that, the nucleus is in the middle, and you have electrons orbiting the nucleus, and some orbiting at a closer distance, some orbiting at a farther distance. As you see here, the orbits, quote unquote, orbits that he drew were they're closer in the nucleus and some further out. And so it turns out the orbit or the closeness of the electrons to the nucleus dictates its energy, right? The closer you are, the lower your energy is. The farther you are from the nucleus, the higher the energy. And each of these levels has different energies, and so they are also called shells. So think about this in terms of the ladder, right? You have different rungs on the ladder. You got the first rung, the second rung, third rung, so on and so forth. Think about that for the analogy of the energy. If you're on the first rung, you have lower potential energy than if you're on the highest rung. And how do we know that? If you do an experiment, if you're on the first rung and you jump down, you won't feel much, right? But if you're in the highest rung and you jump down, you will feel a lot because there's a higher potential energy from the distance from the ground. Much the same way, the lower the energy, the lower the electrons is in this orbit. So the closer they are to the nucleus, the lower the energy. The higher, the farther away they are from the nucleus, the higher the energy. And so we have that here, a way to describe how electrons live in each atom. So for example, carbon. How many electrons does carbon have? So we know that carbon has 6 electrons because it has 6 protons, right? The number of electrons and protons must equal each other if it's a neutral atom. And we know that carbon has 6 protons because it is atomic number is 6. Okay, so it turns out not only do electrons live in these discrete levels called quantize, meaning no electrons can live in like level 1.5. They either live in level 1 or level 2 or level 3, no in the middle. Right? So not only do they live in this discrete levels, but each level has a maximum capacity, right? So it turns out the first level, the maximum it can hold is 2 electrons. The other levels, so level 2 and level 3, it can hold a maximum of 8 electrons. Okay, so if you are carbon, you have 6 electrons. So the first 2 lives in the first level. How many more do you have left? 4, right? So then the last 4 lives in the second level. So we can go ahead and take a look at this and expand it to the other elements. So below carbon, we have silicon, right? So they're in the same column here. So how many electrons does silicon have? Silicon, I believe, is element number 14. I think 14, right? So therefore 14 electrons. So the first two electrons live in the first level, so that's 2. The next level can fit only 8, so 2 plus 8 is 10, giving us 4 more electrons, right? So that's for 1, 2, 3, 4 more electrons on the outermost level, right? So notice here, I've circled in red, I've highlighted in red here the last level. So the last sphere, the last shell is highlighted in red, and they share something in common if they're in the same, if these two elements are in the same column. If they're in the same column, they have the same number of electrons on the outermost shell. And so these electrons are called valence electrons. So valence electrons are just the number of electrons you have on your outermost shell, the outermost energy level. And so this corresponds to a column number. So for example, this is group 14. Remember, there's two ways of saying the group number. Either it's this way, where it's 14, or you take the number and you minus 10. So it's group 4. Okay, so 4A. So therefore, group 4A has 4 valence electrons. Let's take a look further at other examples. So we have here group 1. So guess how many valence electrons group 1 has? It would have 1 valence electron. Very good. Yeah, so you can see here, the first hydrogen has 1 electrons on the first level. Lithium has 3 electrons, so it has 2 in the first level. So the last one must exist on the last outermost level, level 2 there. And then so on with sodium. Let's see the patterns again here. If you are in group 17, remember 17 minus 10 is 7. So group 7A would have 7 valence electrons. And we do see that 1, 2, 3, 4, 5, 6, 7 valence electrons. So it turns out valence electrons is what is important. All of chemistry is dictated by these valence electrons, and here's why. Remember this last group here, group 18? Remember their name? They're called the noble gases. Remember we said that they're called noble gases because they don't want to react. They're like super stable. They're kind of off standish, right? It's because they're not very reactive. They're very happy the way they are. And it turns out everyone wants to be that happy. Everyone wants to be like the noble gases. And what is the driving force that makes them happy, that makes them stable? It's because in their valence electron, they have maximized, they have filled up to maximum capacity. So for example, looking at argon, how many electrons is in its valence electron shell? You got 1, 2, 3, 4, 5, 6, 7, 8. So argon has 8 valence electrons. How about neon? 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electrons, right? What about helium? Helium has only 2, but wait a minute. Remember, this is the first level, and the first level can only hold 2. So it is also very maximized. It's already at the maximum capacity of electrons. So that's why helium, even though doesn't have 8 electrons, is also considered a noble gas. Okay, so everybody wants to be like a noble gas, whether you're a hydrogen and you want to be like helium, or if you are fluorine and you want to be like neon. You want to have the same electron configuration as the noble gases. So there's a name for that kind of wanting. So the rule, if you want to be like 8 valence electron, we call that the octet rule. And so there's some exceptions. For helium, that's called the duet rule. Remember octet? Oct is 8, right? Like the octagon has 8 sides. And then duet, it's 2. Okay, and so we need to be able to do this for 20 elements in our class. If you go beyond this, it gets a little bit more complicated, which at the level of this class, we're not going to dive into. So your job is just to know the first 20 elements. Now, we just talked about how electrons are found to live in different energy levels. So how did they come about this? So to understand the evolution of that concept, we have to understand light. Okay, so let's do a little backtrack here. Light is energy, right? And energy can when we look at energy, we can look at it in terms of its wave-like property. Okay, so I have here a whole spectrum of different manifestation of that energy, of that light. And some of these words you know already, right? Like we said, they are manifestation of waves. So we can see here FM and AM radio waves. You are familiar with that when you listen to the radio. You're familiar with what? Microwaves, for example. That's something in your kitchen, right? You are familiar with IR and UV. You've heard of those terms, hopefully. And then X-rays and gamma rays, right? So all of these are different light, different ways light can be seen, quote, unquote, seen, okay? And we talked about how the difference between these waves is in their wavelengths, okay, and in their intensity. So imagine a calm and cool wave, just like the ocean, right? Calm and cool wave looks like that, whereas a very turbulent wave will look like that. Okay, so I have here a picture that can give you that visualization. So the first feature I want to point out is something called the wavelength. The wavelength is just basically the length between the two peaks of a wave. So if this is the peak of a wave, it goes down and back up, so that it comes back to the same peak, right? So that distance is called the wavelength. So look at this wavelength versus this wavelength, right? So this is a longer wavelength, and on this end is a shorter wavelength. So on the right-hand side, you imagine your waves. In the left-hand side, this is the wave. Based on my hand, which one do you think is more energetic, right? This is more energetic. So on the right-hand side, you have longer wavelength. So the larger this number is, the smaller the energy is. Smaller the wavelength is, the bigger the energy is. So it turns out on this right-hand side, you have things like X-rays and gamma rays. These gamma rays are like rays from a cosmic, from the universe shining in. X-rays, you see it as your when you go take an X-ray, right? So these are very strong energy lights. They are so strong that they are actually damaging to our DNA. They can break the bonds in our DNA and cause diseases like cancer, right? So these you have to be careful with. These other lights, they have longer wavelengths, so they are less harmful to us. But in any case, there is a small slither of the spectrum that we can see. All of these we can't really see, right? But there is a small slither of the spectrum that we can see in this wavelength between 750 and 380. We can see, because this is called the visible spectrum. So in this, when light falls within this spectrum, they can be presented to our eyes, right? So for example, we can see red, orange, yellow, green, blue, and violet, for example. So as you see here, red is more on the right-hand side, so lower energy, and violet is on the left-hand side, so higher in energy. Right, so keep that in mind about the visible spectrum there. And this visible spectrum is what we see in the rainbow. We can see it as continuous. Continuous meaning there's no point where you transition to a different color abruptly. It just kind of bleeds slowly into another color. All right, so let's go back and see how this idea explains to us about the electrons and where they reside. So come back into the idea that electrons reside in what is known as a ground state, right? So all electrons are in a state that they're pretty happy in. And remember, these states are quantized, so they have rungs in the ladder. Now, when these atoms receive some kind of energy, whether that be like electrical current or you burn something, so there's energy from a heat source, it will make these electrons jump into another level. It will jump into another quantized level, right? And so when you jump into that level, you call that the excited state, right? So you absorb some energy, you jump into another state. We call that the excited state versus the ground state. But at this excited state, nothing ever lasts that long, right? So even electrons, they can't stay in this hyper excited state all the time. So eventually they will need to go down back to their original state, the ground state. But as they go down, that gap in energy that is between the excited state and the ground state, it needs to release an energy in order to go back down, right? So you imagine super hyper to go back down to a lower energy state, you have to release some kind of energy. Same thing with electrons. You're going to release a certain energy. And that gap, that energy can be a big energy gap or a small energy gap, right? And so that energy gap, if it's big or small, will result in different light. Whether you are in high energy, so you release something that's like in the violet color range, or you're low energy, which is something in the red range, and anywhere in between. So let's go back and talk about how we can excite these electrons. So we have here examples where we have noble gas elements, and they're gases, right? So we put them in a tube, a light tube, and then we run electrical current through them. As they get excited, the energies, the electrons then can go from excited state back down to the ground state, releasing energies to us, releasing light to us. So helium, as you see here, looks like purple, or neon looking like red, and then xenon here looking very nice blue there. Another way we saw that is burning. When we burn chemicals, they can also release fires that are very colorful. So for example, if you burn lithium, that same phenomenon happens, but in this case, lithium will release or is observed to have red colors, sodium, that orange color, potassium, that purple, so on and so forth. And it turns out these this property actually is how fireworks work. We put different elements into the firework compounds. We throw them in the air, and then we explode them. And as they explode, we burn them. They will release different colors based on the elements, based on the excited electrons going down to the ground state of different elements. So again, how does that relate to knowing where electrons live? So we need to understand this, how light can be seen through a prism. So if you shine light, like the sunlight, right? You don't see it as a color, but actually it contains all of the visible colors. So for example, if you put a light through a prism, this glass that can kind of diffract and split up all of the different individual light and all of the individual energies in that light, you can see the continuous color change, which is known as the continuous spectrum, which is like the rainbow, right? So when it rains, but you can still sunlight can still shine through. Sunlight, when it goes through the rain, is split up by the rain, and therefore forming this continuous color scheme called the rainbow, which is basically the spectrum, the visible spectrum. Right? So if we do that, though, not of visible light, but of like the light we saw earlier from a particular atom, particular element, we can see that each element, because it has a different number of electrons and their configuration, will give us, so those different electrons configuration will have a different pattern of jumping up and then coming back down, releasing different type of lights. We can then calculate where they live. And of course, we won't do it in this class, but that's just the idea. So for example, if we take cadmium here and we excite it and then observe the light that it emits out, it will look like this. It would have many electrons that give off this color of blue and green, and some of this yellow and some of this red. Notice that it's very discrete, right? So these are lines as opposed to a continuous spectrum like sunlight. So elements, because they have discrete quantized energy jumps in electrons, they will give us discrete lines in this visible spectrum. So this is a proof for that. So if you do this for every element, you will see something different. And so much so that it's almost like the fingerprint of an element. Actually, this is how, kind of a tangent here, this is how we know, even if we haven't been to a certain galaxy far, far away, or a star far away, we can still know what is the primary elements in that place, because we can submit the light that's shining through and split it up and kind of deconvolute, kind of tease out the splitting patterns, the line spectra in order to know, okay, that universe has a lot of helium, or that universe has a lot of hydrogen, for example. Okay, so basically this is called a line spectra, and it gives us information on where electrons live. Of course, this is a lot of math, very high level. We're not going to calculate this. It's just for you to know how we know electrons and where they are. Okay, so comes back to our Bohr model focusing on the valence electrons. Okay, so the faster way of doing it is to know the columns where those elements are, because it corresponds to the number of valence electrons. So like I said, if you're in column 1A, you have one valence electron. This is the quick way. And instead of drawing the Bohr model for every single element, and then seeing what's on the valence, on what's on the outside, to get the valence electrons, you just look at the periodic table and say, what column are they in? If they are in the first column, 1A, one valence electron. In the second column, 2A, two valence electron. Third column, three valence electrons. 4, 5, 6, 7, etc. All right, and then again, we also mentioned before that everyone wants to be like the noble gas, right? Everyone wants to have the same electron configuration as the noble gases. So for example, if we take sodium here, how many valence electrons does it have? One valence electron, right? So because of that, it can give off one, if it gets rid of that one valence electron, it would have, what's the level below that one valence electron? 8, right? So then it can look like a noble gas if it gives away one valence electron. Now, if it gives one valence electron away, it has more protons than electron, exactly one more proton than electrons. So that's why it's a positive 1. So that's why all of these elements, when they give off electrons to become a noble gas configuration, they will be positive 1. So 2A will always be 2 positive. 3A's will always be 3 positive. So the first 3 will lose electrons and therefore be positively charged. Whereas group 5, 6, and 7, think about this. If you are, let's say, fluorine, is it easier to lose 7 electrons to become like helium, or gain 1 more electron to have that 8th electron? It's easier to just gain electrons, right? So the elements on the right-hand side, so particularly groups 5, 6, and 7, will gain electrons to become negatively charged. Whereas groups on the left-hand side will lose electron, becoming positively charged. So we'll take a look at this in closer detail now. So the first, and we'll break it into 2 groups, the positive charge and the negatively charged atoms. The first one is the positively charged atom. So let's take a look at sodium here. Like we said, sodium is element 11, so it has 11 protons and therefore 11 electrons. So 2 electrons on the first level, 8 electrons on the second level, and 1 electron on the last level. So it will give 1 electron away, then it will look exactly like neon, right? So here we go, that one electrons, if it goes away, it looks like this, whereas 2 and 8. So it's like a noble gas, neon. Now let's take a look at the charge count again. Remember, we have 11 proton because it's element 11. It has 11 electrons. So as an element, it is charged 0. So 11 positive, 11 negative equals 0. So neutral. If it gives away 1 electron, it has only 10 electrons left. So 11 positive, 10 negative. So that's a positive 1, which is why we say Na positive. When if it's just 1, we just put a positive. We don't say positive 1. It's assumed positive 1. All right, so we see right here, sodium atoms, neutral, can become sodium positive charge once it releases 1 electron. So to differentiate between the neutral and the positive charge forms, we call this a sodium atom, but we call this a sodium ion, right? So ion. And if it's an ion are basically atoms that are charged. If that ion is positively charged, we call it a cation. Note that these 2 substances are quite different from each other. So sodium as a metal, as just an atom, neutral atom, looks like this, regular metal, right? Shiny, solid. all right? But once it transforms itself into an ion, it's totally different, right? It's actually not even visible anymore. Like in sodium chloride, it just dissolves and disappears into the water. So this sodium is a sodium ion. This sodium is a sodium metal. The chemical character, the property of sodium is quite different depending on whether it being neutral or whether it being an ion. Now let's take a look at the other ion, the anions. So for this example, let's take a look. The classic is chlorine. Chlorine is element 17, so it has 17 electrons. First 2 electrons on the first row, 8 electrons on the second row, and 1, 2, 3, 4, 5, 6, 7 electrons on the 7th row. So it has 7 electrons on the outermost shell. So it needs 1 more to be happy, right? Rather than losing 7, it can gain 1. And so it does so to become argon. So it has 8 electrons on its outermost shell. Now notice when we do that, it is no longer neutral because it has an extra electron, 18 electrons. So overall it has a -1 charge, so we write it as Cl-. And then to differentiate between the chlorine atom and a chlorine negatively charged atom, we give it a different name. Instead of calling it a chlorine, we call it a chloride. So cations don't have this name change, but anions will have this name change. Okay, so anions, when they are an anion, elements on the right-hand side, when they become an anion, they will drop their INE ending and add in IDE ending instead. So chlorine becomes chloride, fluorine becomes fluoride, bromine becomes bromide, oxygen is now oxide, sulfur is sulfide, nitrogen becomes nitride, phosphorus becomes phosphide. Okay, so basically those are the ones that you will have to know. Iodine is another one, becomes iodide. Just like how different sodium element is from sodium ions, chlorine is the same way. Chlorine as an element is actually a gas. This yellow gas here is used as a chemical warfare weapon in World War I, right? So it's quite toxic. Whereas chloride ion, not so. As we see before, it is the second component in sodium chloride in your IV bag, in your saline solution. Okay, and so these two are prime examples because when a cation and an anion come together, they form a very strong bond called the ionic bond. They love each other, right? And in this situation, there's always one that's giving and one that's receiving. That's why they fit so well together. So the metal will tend to give electrons to become the cation. Well, if you give, someone has to receive, right? So the non-metal will receive the electrons, becoming negative anions. So here, as an example, we said that sodium has 1 electron left in its valence shell. It wants to get rid of it to obtain 8 octet. When it gives it away, it has to give it to somebody. It can't just like give it, right, into thin air. Someone has to receive for it to give. So luckily, chlorine nearby is hunger for 1 more electron. So they're perfect for each other. Match made in heaven, right? So therefore, this 1 electron is given away to this chlorine. So both of them are happy. It's a win-win situation. They both become fully octet. So much so that they are attracted to each other if they become something called sodium chloride. In the previous image, we showed how sodium chloride is a solution. That's because it's dissolved in water. If we remove all the water out, they actually become solid, like you see in your table salt at home, granular solids, or they can be organized in a crystal, like this sodium chloride salt crystal. So let's revisit that idea again with a different perspective here. We see here that sodium has 1 electron on the outermost shell, so it wants to get rid of it for an octet. Chlorine has 7 electrons in its outermost shell, so it also wants to be octet by receiving an electron, so they're perfect for each other. So that happens. Once sodium gives away its electron, it is positively charged because it has more protons than electrons. Once chlorine receives that electron, it becomes negatively charged because it has more electrons than protons, right? Now, what do you know about things that are opposite from each other? Opposite attracts, right? That's kind of like a rule of nature. So yes, this positively charged cation is so attracted to this negatively charged anion. And because of that, they form a very strong bond. They stick together very strongly to form a solid. And again, the driving force for this is to form an octet. And it turns out that sodium atom as a metal versus chlorine gas as both elements are not as stable as when they become a salt, become ionic salt of sodium and sodium chloride. And so that's the driving force for this reaction and to become octet. All right, so having said that, there is a way to draw this interaction in a simple and faster way instead of drawing all the electrons out. Lewis is a scientist who just want to focus on the valence electrons. So instead of drawing Bohr's model, he just simplifies it and get rid of everything except for the last valence electrons. And so this model is going to be important to us for next unit also, but I'm going to introduce it here. So Lewis just says that we want to draw electrons around the element. So we can draw it on the sides and the top and the bottom. So sulfur, for example, has how many valence electrons? 6, right? So we can draw 6 valence electrons by first, and you can draw the electrons in any position first, doesn't matter, as long as you fill the sides first before you double up. So here's what I mean by that. So sulfur has 1 electron, second electron, third electron, fourth electron. So there's 1 on each side, right? Once you have filled up once on each side, then you can double up. It has 2 more electrons, so you can double up the top and double up the bottom, or you can double up the side. Doesn't really matter. The only key here is that you need to fill each sides first before you double up. And the maximum you can fill an electron each side is 2 electrons. So keep that in mind. So that's sulfur. So let's go back to look at our 2 examples that we looked at previously. So sodium has 1 electron, so you only draw as 1 electron on the right-hand side. Again, it doesn't matter left or right or top or bottom. Chlorine had 7, so it looks like that. Once sodium gives away its electron, you can draw it like that. So sodium is now, you know it's naked without any electrons, but then therefore you know that it has 8 electrons also as its octet, but we can draw it without electrons. Whereas chlorine, now you can see clearly that has 8 electrons in its Lewis dot structure or dot symbol. All right, so we said all of these elements will come together because there's a driving force for the octet, and so they form something called something called ionic compounds. So because they form these ionic compounds, they're quite prevalent, so you'll encounter them a lot. So let's talk about how they kind of come together and what do they make. Okay, so there's a pretty good rule to follow. 2 main rules I want to focus on here is the first rule is it always happens between cations and anions. And cations are mostly metals and anions are mostly nonmetals. The second rule you want to follow is that you always want the total positive charge to balance out the total negative charge. They add up to become 0. That's neutral. Nature always wants to be neutral because that's the most stable. So let's talk about this by looking at examples. Our classic example is sodium and chloride, right? So we have sodium is an Na positive 1, and chloride is a negative 1, Cl negative 1. So do they add up to become neutral? How many and how many? If you have 1 sodium and 1 chloride, 1 positive, 1 negative, positive 1, negative 1, add them together is 0, right? So you only need 1 of each. So that's why it becomes sodium chloride as NaCl. You don't write a subscript of 1 if there's only 1. Okay, so that's why it's just NaCl. There's no subscript of 1. Now, does that mean in salt there's only 1 sodium and 1 chloride? No, right? It's just a ratio. There could be billions and billions of them, but the ratio will be the same. If there's a billion sodium, there's a billion chloride. The ionic formula talks about the ratio between the ions. Let's do another example. What about this one? Let's take a look. Magnesium, when it becomes an ion, is in the second column, so group 2A. So it becomes magnesium 2 plus, right? And then chloride, we already know is Cl minus, so -1. So how many of each do you think is required, the ratio, to be charge balanced? Hopefully you would say you need 2 of the chlorides, right? Because each one is -1. So if you have 2, then it's -2 charge overall, total. Whereas magnesium, if you have only 1 magnesium, it's already 2 positive. So 2 positive, 2 negative becomes 0. So you would need 2 of the chloride ions, right? So how do we write that? We put a subscript 2 after chloride. So we write as MgCl2, and we call that magnesium chloride. So going back to talk about the names here, when we talk about the name of ionic compounds, we just say the cation name, as in its element. It doesn't change. So magnesium just becomes magnesium. Chlorine, though, is an anion, so we change its name to IDE, so chloride. Chlorine becomes chloride, okay? And notice that there's no number 1 under magnesium, because 1 is just assumed there. If you don't write 1, we assume 1 is there. Just like chlorine, we don't see a Cl minus 1, right? We just say Cl minus. All right, one more example. Oh, before we go to that example, notice that there's a common trend here. If this is 1 and this is 1, you bring this 1 down and you bring this 1 down, so it's a 1-to-1 ratio. This is 2, you bring it down. This is 1, you bring it down. So that's 1, 2, a 1-to-2 ratio. So that shortcut works most of the time, but it doesn't all the time. So just double check. So here's an example where it doesn't work. Magnesium, again, we know it's 2 positive. What about oxygen? Oxygen is in group 6A, so it's an anion. It gains 2 electrons, so it's a 2 minus. How many of each do you think is needed to become neutral? Hopefully you said 1 of each, right? So you would write this as MgO. Very good. And you would call it magnesium oxide. Notice in this case, the shortcut doesn't work. You can't just put 2 down and 2 down and write Mg2O2, because the ratio has to be the lowest ratio. So a 2-to-2 is the same as the 1-to-1. The lower ratio is what is needed. So we write it as just 1-to-1. Because remember, it's not 1 atom of this with 1 atom of this. It's just a ratio. It could be a billion of this, but the same amount of oxygen. Okay. All right, so there we have it, ionic formulas. So those are when the cases are kind of simple, where you just have 1 element of cation, 1 element for anion. There's another case called polyatomics. So ions can be composed of multiple elements. Okay, so let's take a look at this. But the rules are the same. The 2 rules that we followed before are the same. Our first example here is aluminum is by itself, right? So that's common, or that's the one we've seen already. This is the new one. This is polyatomic. So this 1 ion, and it's an anion because of the negative, this 1 anion is composed of 1 phosphorus and 4 oxygen atoms. Together, it is a polyatomic with a negative charge of 3 minus. Okay, so treat it just as if it is a single element with a charge of 3 minus. Ask yourself then, what's the ratio between these two? How many of this do you need? How much of the cation do you need to charge balance with the anion? Aluminum is 3 plus. This thing is 3 minus. So they are already charge balanced if you have just 1 of each, right? So you just need 1 of each. And you can write it as aluminum and then the whole parentheses, and then drop. Remember when we write the formula, we drop all the charges. So we have 1 aluminum and 1 phosphate. So you can write it like that and call it aluminum phosphate. Now in a higher level chemistry class, the professor is probably more picky. Anytime the polyatomic has a subscript subscript of 1, you should get rid of this parentheses. But in this class, you can keep it. It's fine. Let's do another example. So that was an example where the anion is a polyatomic. Let's take a look where the cation is a polyatomic. But it's the same thing, really. So we have here ammonium ion, which is composed of 1 nitrogen and 4 hydrogens, and together they are positive 1 charge. On the other hand, our partner is a sulfide, which is a 2 minus. So what's the ratio, do you think? Do test yourself here. What's the ratio do you need to be charge balanced? Hopefully you said you need 2 of this guy. So 2 ammoniums for every 1 sulfur or 1 sulfide. And you would be correct. Since you need 2 of the ammonium, you just need to write the subscript of 2 after the parentheses of ammonium. And so this molecule will be, or this compound will be called ammonium sulfide. And those are the first 2 examples of polyatomics, but here's the whole list of polyatomics that I would require you to memorize for this class. So you would have to know the name and the formula and charge for them. So it's best to make flashcards to start to kind of challenge yourself to memorize these polyatomics. So we have here ammonium, acetate, bicarbonate, hydroxide, chlorate, hypochlorite, cyanide. We also have nitrate, nitrite, carbonate, sulfate, sulfite, phosphate, and phosphite. So notice there are some similarities among these. Like phosphate and phosphite are very similar names. That's because they are basically polyatomics of oxygens with phosphorus, right? But just have a different number of oxygens. Or same thing with sulfate, is they both have sulfur in it, but just different numbers of oxygen. Same thing with nitrate and nitrite, different number of oxygens. Chlorate, hypochlorite, same thing. Notice that all of these polyatomics tend to be negative, so they're anions, and there's only really 1 cation that you need to know. And then if you look at like chemical ingredients that you have, there are many, like in a soda can or like food items that you have at home. There are many different polyatomics that's not even listed here. Like for example, citrate, right? It's an anion form of citric acid, basically. So there's a lot of polyatomics, but we don't have to know all of them. Just know these for this class. All right, so I'm going to end our lecture today to give you some perspective about where you can find these in your everyday life. So for example, when you use baking soda, the main ingredient in there, or probably the only ingredient in there, is sodium bicarbonate. So you will use this to clean your house, or even put a batch of this in your fridge to get rid of the odor, because it absorbs the odor in your fridge. All right, and another cleaning agent is bleach. And if you zoom into the ingredient list here, you will see that the main ingredient is sodium hypochlorite. So both of these ingredients, the cation is what? Sodium. And this one, the anion is bicarbonate. And this one, the anion is hypochlorite. The last example I'll give you here is when you have an upset stomach, you ate too much that day, or you just have acid reflux, then you might want to calm that down by taking Tums, which is an antacid. There are many different forms of antacid. The most prevalent form is calcium carbonate. So in this one, the cation is calcium, and the anion is carbonate. So I would expect you to know how to write the formula for this, like calcium carbonate, for example, or sodium hypochlorite, or sodium bicarbonate. Okay, so do a lot of practice with this and kind of explore in your kitchen cabinet or in your bathroom cabinet, or even in your garden to see if you see ionic compounds all over the place. All right, so that ends it for us. And next week we will move away from ionic bonding, but we're still going to stick to bonding, but move to covalent bonding. Okay, so until then.